Hi, I'm Catherine Byerts, and I am the Group 1 reporter for the Rankine cycle experiment. Theoretically, the Rankine cycle happens between a boiler, a turbine, a condenser, and a pump. And for our purposes, there's 4 points that have important properties about them that you need to observe. Work, obviously, or energy comes into the boiler, into the pump, and the turbine and the condenser both move energy out of the system. The PV and TS diagrams are shown here are the theoretical movements of pressure and temperature along specific volume and entropy for these 4 points. And you can see that the pressure 2 and 3, that would be going through the boiler doesn't change, and 1 and 4 doesn't change, the condenser pressure doesn't change. So you can use some of those properties to evaluate your data once you get it. And that's going to come into play later. So this is just a little more about what's happening at each of these points. So the pump pressurizes the water and gets it ready to go in the boiler, and you can calculate the energy balance using the change in enthalpy between 1 and 2. And then the boiler boils the water, brings it to a superheated vapor, and again, you can calculate it with the enthalpy. And the superheated vapor goes to a turbine, where it expands and discharges, and it produces work through the turbine. And then it goes into the condenser to bring that steam back into a liquid to go back into the pump to the boiler. Start all over again. So that's just, this equation is just a general energy balance for the system, for the heat and work going in and out of the system. Obviously, theoretically, it equals 0, but it doesn't, when you do it, obviously, it equals 0. And the efficiency can be theoretically calculated using those changes in enthalpy that you can get from your steam tables once you know your pressure and temperature at your 4 points. So this was the setup that was in the lab that was not working. So we didn't actually get to use it, but we got to look at it. And so that's basically the diagram on the previous slide. So for data reduction, there's going to be a series of plots, and the black box indicates the steady state time where the plots were relatively steady. And there's going to be a red X on each of the plots, and that is where I pulled my data to calculate my properties at each point. So, that was fuel flow in time. The boiler temperature, which was a steady rise. Boiler pressure versus time. I'm not quite sure why some of the changes in some of these graphs happen, because we obviously didn't take this data ourselves. So inlet exit pressure of the turbine, and inlet exit pressure inlet exit temperature of the turbine, and then the amperage of the generator, voltage, the RPM of the turbine. And so these, at my point, I took these, or my steady state point, which was about 400 seconds, I took these measurements. You can see that, one of the points of the experiment was to keep the boiler around 110 psi, which was achieved fairly well. And what should be noted is the turbine inlet and outlet temperatures were shown here about 170 to 200, and the boiler temperature was 285. And so that becomes an issue later, because when I went to calculate this, the inlet and exit of the turbine were obviously given with the data, and based on those theoretical charts, I could say that between 2 and 3, the pressure was supposed to be steady, the same, and between 1 and 4, the pressure was supposed to be the same. But whenever I tried to use either the boiler temperature that was recorded and in that data that was given to us, it did not make any sense compared to those charts. Even the difference between a real cycle and ideal cycle. It didn't match up at all. And I also didn't really like the values that came out of the steam tables when I examined those for these points. And so that didn't make sense to use either, so I left it out because I really was not sure how to reconcile that, and I spent a good amount of time trying. So these are my calculations. I'm not quite confident in them because of that issue that I had with the two temperatures that I couldn't figure out. So this is just calculating the work put out by the heat being put into the boiler and the work from the turbine. This is all just to calculate that efficiency. These are the things you need, and so and you need your value from the condenser and the pump. I chose to use actual values and not the specific ones, so I went ahead and multiplied by the mass for each of these. And my cycle efficiency came out to be 0.8%, which really, I hope that's not right for the sake of that setup. But theoretically it should be 100. Obviously you're not actually going to get it there. So in conclusion, obviously it's not an ideal cycle, and there's probably errors in instrumentation and maybe readings taken by people, but it's not our data, so I'm not sure. Any questions?
Both of you use the same data, is it?
Yeah.
Can you go to your data sheet?
This?
Yeah, your boiler temperature is 285. Here used 276.
Oh, it's different times.
Well, yeah, so he took his steady state time at like 350 seconds, I think his was at, and mine was at 400. It just said to pick a point within the steady state time frame, so I'm sure that's where it was from. Because if you looked at like all these graphs between 350 and 400, there's obviously like, it's relatively steady, but not perfectly.
Okay. Can you go to your first plot?
This one?
So what is the units for your fuel flow and time?
Yeah, I realized I didn't label anything. I believe that that's liters per minute and seconds.
That's important.
Yeah, I skipped that.